Greetings YouTubers, I am Rick the Tech Enthusiast here with the next Elegoo Lesson number 17, HC-SR501 PIR Sensor. In this lesson, we'll check out the HC-SR501 PIR Sensor that is provided with the Elegoo kit. We'll build and configure a simple circuit that is provided in the tutorial to demonstrate the functionality. Then we'll build a custom circuit to provide audio and visual indications. So let's start building. The HC-SR501 PIR sensor that is included in the kit is a passive infrared sensor and one of the few sensors that can do work without the Arduino. First, you'll notice that the unusual looking dome. That dome is comprised of Fresnel lenses that focus the infrared light onto the sensor. The piezoelectric sensor, which is located underneath the dome, has two slots that detect infrared. Like when a person passes nearby, infrared light strikes one of the slots before the other, causing a positive or negative differential change, activating the sensor's output. Underneath, you can see the time delay and sensitivity potentiometer adjustments. From the datasheet, the time delay can be varied from 5 seconds to 300 seconds, or 5 minutes. Though the tutorial indicates a minimum of 3 seconds. Rotating the potentiometer clockwise or right will increase the time delay to a maximum of about 5 minutes. Adjusting it counterclockwise or left will decrease the time delay to a minimum of about 3 or 5 seconds. And I found that my minimum time delay is around 2.7 seconds. The sensitivity potentiometer adjusts the range from about 3 meters up to 7 meters. Rotating it clockwise or right will decrease the range to a minimum of 3 meters. Adjusting it counterclockwise or left will increase the range up to 7 meters. The jumper, shown here on the right, switches the sensor trigger from low to high. Low indicates a single trigger, while high is a repeatable trigger. The bottom pins are VCC, output, and ground. VCC or power can be anything from 4.5 volts to 20 volts. The output pin is 3.3 volts when the sensor is triggered, which should also be enough to trigger the 5-volt system. Otherwise, it is 0. Now, what's hardly mentioned in the datasheet is there are 2 sets of through-hole connections for optional sensors. The upper left one is for the temperature sensor like a thermistor. The lower connections, just above the pins, are for a light sensor like a photoresistor. The tutorial indicates that the sensor's viewing area is 110 degrees. The datasheet indicates 100 degrees. Regardless, that area is from the top of the dome and not necessarily the sides. In addition, the sensor needs about 60 seconds to settle down once it's initially powered on. For about a minute, no sensor activation can happen. And also after the time delay, the output goes low and will not trigger for about 3 seconds. Though I found that my sensor takes about 6 seconds. All of this may seem a little confusing, but here's how it works. Imagine that the PIR sensor's time delay is set for 3 seconds, and the jumper is set to low for a single trigger mode. First, we power up the sensor. The sensor will wait for about 60 seconds before it can trigger. Afterwards, if triggered, the sensor will hold the output pin high for the adjustable time delays 3 seconds. Then the output pin will go low for 3 seconds, or in my case, 6 seconds, during which no trigger event can occur. This is the wait time delay. Then the sensor is ready to trigger again. Now, if we set the jumper to high, or repeatable trigger mode, and after the initial wait period, the sensor, if triggered, will start the time delay as before. However, this time, it can be triggered again, which will reset the adjustable time delay. If it finally doesn't sense any more triggers, and when the time delay is completed, the sensor will drive the output low for 3 seconds. This is the wait time, or the wait time delay, during which no trigger event can occur. In either case, these events happen without the Arduino's control, Really, the only thing we could do is monitor the output. The datasheet and the tutorial have additional information on the HC-SR501 PIR sensor, and I encourage you to check them out. For this lesson, we'll need the following items from your kit: the Elegoo Arduino UNO R3 board, the HC-SR501 PIR sensor, 3 female to male jumper wires. On page 128, you'll see the following schematic. A jumper will be connected between the output pin and pin D7. Then they're just power and ground. Super simple. On page 129, you'll see the wiring diagram with a photo on page 130. Note, we're not going to be using the breadboard. We'll just directly connect the jumpers between the Arduino and the PIR sensor. Okay, let's jump to the code. As before, we'll load the recommended sketch provided in the tutorial. Go to the File menu item, select Open, and browse to where you saved the Elegoo files. Then under your language, Code, under Lesson 17, HC-SR501 PIR Sensor, HC-SR501, and open the HC-SR501.INO file. Looking at the code, you'll see, wow, there's nothing to it. It starts by setting 2 global variables, LED pin and PIR pin, to their pin values. The third global variable, integer PIR value, which will be used to store the PIR output value. The void setup sets the pin modes for the LED pin and the PIR pin to output and input. Then it performs a digital write to the LED pin, setting it low. The void loop starts by getting the PIR pin value and then setting the variable PIR value. Then it performs a digital write to the LED pin, passing the PIR value to either turn it on or off. Remarkably simple. Let's upload the code and try it out. All right, it uploads. And you see the built-in LED turns on. And then it's triggered. 1, 2, 3. You can also see that it doesn't respond in between times, so there's no repeat trigger. Then it's triggered again. 1, 2, 3. Triggered again. 1, 2, 3. Well, that previous sketch, though it showed the functionality, was a little too basic. Let's make a new circuit with some LEDs, a different one for each state. Oh, and let's add a buzzer, because it would be cool to add some audio confirmation too. So I've come up with this PIR sensor circuit and sketch to better illustrate the different PIR sensor states, provide an audio and visual indications, and provide actual timing values to the serial monitor. The schematic is simple. The PIR sensor is connected to the 5 volts and ground rail. The output is connected to pin 7. The red LED is connected to pin 8 through a 220 ohm resistor and to the ground rail. The green LED is connected to pin 9 through another 220 ohm resistor and to the ground rail. The blue LED is connected to pin 10 through a 220 ohm resistor and to the ground rail. Finally, the active buzzer is connected to pin 11 through a 100 ohm resistor and another pin to the ground rail. Looking at the wiring diagram, you can see that the resistors span the center gap to connect to the 3 LEDs and buzzer to the various pins. I used orange and yellow jumpers to span the center gap and connect the ground rail. The PIR sensor is connected to the positive and negative rails and to pin 7. The sketch begins with several constants to define the LED pins, buzzer pin, and detection constants that will be used to differentiate the sensor states. Then some constants used by the sketch, like the buzzer on time, initial delay, and such. The unsigned integer allows for numbers greater than 32,767. Then the global variables are used to hold or track time and state values. The wait delay is given a large initial value, knowing that we'll be adjusting it later with the software. The void setup begins by starting the serial monitor. Next, pin modes are defined for each output LED, buzzer, and input PIR pin. Then we begin the 1-minute delay to stabilize the sensor. To get confirmation that things are working normally, a for loop is used to create progress dots across the serial monitor during the initial wait time. The extra if statements add a line return after the number of dots defined by the dot length variable. After it's done, I call a subroutine show LEDs, passing the constant sensor state ready. Show LEDs is a simple subroutine to switch on or off the LEDs according to the LED state. First, it sets the PIR state with the past state value. Then it uses switch statements to send a message to the serial monitor and uses digital writes to LED outputs to set them low or high. In this case, the message to the serial monitor is ready, detect LED and wait LEDs are set low, and the ready LED is set high. The void loop starts with its own static I local variable, which is used for progress dots later in the void loop. The static local variable, rather than a global variable, is used here because this variable is really only used by the void loop and it needs to retain the I value. Then it starts with its own switch statement using the PIR state. If it is ready, it performs a digital read on the output sensor PIR pin, passing the values to the variable PIR value. Now, if the PIR value is high, that means the sensor detected an infrared motion and calls the subroutine PIR triggered. Subroutine PIR triggered starts the process of the triggered state. First, it captures the trigger start time using the millisecond function, or millis. Then it calls the show LEDs subroutine, passing the constant sensor state triggered. Subroutine show LEDs sets PIR state to triggered, switches to the triggered case, sends triggered message to the serial monitor, turns on detect LED, and turns off ready LED and wait LED, and then returns. Back at the subroutine PIR triggered, it turns on the buzzer, sets the Boolean buzzer on state to true, and sends a message to the serial monitor measuring delay. Back at the void loop, the break exits the switch statement and the void loop begins again. This time, the switch statement goes to the triggered case. During this time, PIR output will remain high until time delay is passed. If repeatable trigger mode is enabled, the time delay will be reset. The first if statement is used to pass dots to the serial monitor in certain time frame intervals defined by the divisor constant. This allows us to see the progress dots on the serial monitor. Next, the PIR pin is checked and passed to the PIR value variable. If the PIR value is low, which means that the time delay has ended, it records the wait start time and the actual time delay, sends the new value to the serial monitor, and calls the subroutine show LEDs, passing the constant sensor state wait. Let's assume that the PIR value is still high. The next if statement checks if the buzzer on state is true and the appropriate time has passed. If it has, then the buzzer on state is set to false and turns off the buzzer. The break exits the switch statement and the void loop loops again. Okay, the PIR state is still triggered. This time, if the PIR pin is low, it sets the PIR value to low. The subroutine shows LEDs is called with the pass constant sensor state wait. The subroutine show LEDs sets the PIR state to wait, sends the message wait to the serial monitor, turns off detect LED and ready LED, and turns on wait LED. It then returns to the void loop. The break exits the switch statement and the void loop begins again. This time, the switch statement goes to the wait case. The if statement here makes progress dots across the serial monitor in certain time intervals. The next if statement checks to see if the wait delay has passed. If it has, it will send the wait delay time to the serial monitor and call the subroutine show LEDs with the constant sensor state ready value. The next line reads the PIR pin, setting it to the PIR value variable. If the PIR value is high, that means that the wait delay is less than the stored value and the sensor has been triggered. Here's where the code auto-corrects. The new wait delay value is set. The pre-triggered message is sent to the serial monitor along with this new wait delay value. Then the subroutine PIR triggered is called to begin the triggered state. The void loop keeps looping through until the wait delay has passed or the pre-triggered is detected. Then it's back to the PIR state ready, and the process starts all over again. The added value of the serial monitor is that it allows you to record the various time delays and fine-tune your PIR sensor sketches. Let's upload the code and check it out. As you can see, the sketch starts off with a message to the serial monitor. Wait 1 minute to stabilize the sensor, followed by the progress dots across the serial monitor, and the red LED is turned on. Print lines are used to keep the progress dot rows nice and neat. You can see I'm hiding behind the doorway. After a minute is done, ready is sent to the serial monitor and the green LED is turned on. The triggered sensor starts the buzzer for about a half a second. The actual time delay is 2,796 milliseconds. Since I didn't try to pre-trigger the sensor, the wait delay keeps the initial 7,000 milliseconds. The wait state is enabled, the red LED is turned on, and the wait delay is started. This time I tried to pre-trigger the sensor. It didn't work. Again, I tried to pre-trigger the sensor. It worked! The new wait delay is 6,271 milliseconds, and the triggered state is automatically switched on. I tried it again, but this time it didn't work. The new wait delay was sufficient. Still no change. The new values are still working. Okay, now I'm trying to see how sensitive the sensor is. It's pretty sensitive. This time I tried to slowly move my hand to trigger the sensor. Huh, nothing. That's pretty good. I know I've seen the wait time closer to 6 seconds. Let's give it another try. Excellent. The new wait time is 6,077 milliseconds. Well, that's it for this lesson. I hope you've enjoyed learning a little about the HC-SR501 Passive Infra-Red Sensor. If you like this sketch, be sure to let me know in the comments section below. I'll have additional links for other interesting videos and code for this project in the show notes below. Join me next time for Lesson 18, Water Level Detection Sensor Module. If you like this video, don't forget to rate and subscribe. Thanks, and see you next time.